All right, we're going to take a look at systems that oscillate today. There's really two basic systems that you're going to want to know about. One is just a mass on a spring. If you just hook up a mass to a spring, and we'll put it on a frictionless surface, or you can say there's wheels under this thing, and you pull the thing over and it'll bobble back and forth. So mass on a spring. The other one is just the mass on the end of a string or a pendulum, where you pull the mass up and let it swing back and forth. So we're going to look at those two systems. The way to get started with mass on the spring to learn how it's going to move is you want to think about what forces are acting on it. Well, if we're just interested in kind of the horizontal motion, the only force that's going to be relevant is the spring force, which looks like this. F is minus kx. The minus sign is there to remind you that when x gets bigger as you pull to the right, the force is backwards and it's getting bigger with x. So if there weren't a negative sign here, what would happen is the force to the right would get bigger as you pulled to the right, and then the thing would just fly away and never come back. So you really do need to have that negative sign to restore it to its original position. Likewise, if x is negative, you can see then that would make the force positive and wanting to come back this way. So what you then want to do to learn how it's going to move is you want to apply F equals ma. So what our goal is going to be here, our goal is we're going to get position as a function of time, velocity as a function of time, and acceleration as a function of time for this mass. And so what you do is you start with F equals ma, and so you say, well, the sum of all forces on this thing is ma. And so the force, the only force that's really acting on it is the spring force. So we'll say minus kx, the spring force, equals m. Now if I put an a here, there will kind of be like too many time wiggling variables because x will be changing with time and a will be changing with time. So it would be kind of like one equation with two unknown things in it. So it's better if we can write it in terms of just one thing. So what you want to do here is instead of writing a, what you want to do is write it in terms of x, which, as we know, a is the second derivative of the position function with respect to x. So d squared x by dt squared, right? So what I'm going to do is rearrange this a little bit and basically solve for this term d squared x by dt squared. So you get d squared x by dt squared, which really is just the acceleration, equals minus k over mx. So what this thing is this is what's called a differential equation. In a normal algebraic equation, you don't need nothing to write down here, but just to sketch something to talk about. If you had something like 2x plus 1 equals 9, right? Well, you know the answer, or the variable x must be 4 in this case, right? So that's an algebraic equation. Solution's like a number, an expression, or something. In this case, the solutions to what's called a differential equation are functions, x of t. So in English, what this is saying is there's a function out there that if you take two derivatives of it, you get the function right back. You get the same function back, but it just has a negative constant in the front. So you kind of need to think about something that if you take its derivative twice, you get it back, but with a negative constant in the front. So one solution that I can propose to you is this. Well, I'll write it down first, then we can talk about it. X of t is, so I'm just going to propose one. A cosine root k over mt plus a phase. Right. So I propose that is a solution to this equation. Well, the way to check if that's, how do you know if I'm telling the truth about that? Well, let's just try it and see if it works. Okay, so we'll try to plug it in. Well, so if you take one derivative with respect to time of this, dx by dt, that would be the velocity, as a matter of fact, if this were x of t, v of t. And so let's take one derivative of this function. Well, so the derivative of cosine is negative sine. So you get negative, leave a little space, you'll see a sine of all this stuff, root k over mt plus a phase. Now we're not quite done because when we're taking the derivative of this thing, we need to apply the chain rule. So we have a function within a function. So root k over mt plus delta is the inner function. And so we need to take the derivative of that, that argument of the cosine. So you can see the derivative with respect to time here is just going to be root k over m. And so that's going to go in front. So that's just applying the chain rule. Root k over m. So there's our velocity function. If this is a good solution, let's then take one more derivative with respect to x. D squared x by dt squared equals. So what we need to do is take one more derivative. So we know the derivative of sine is cosine. So you get this a cosine. Here's your negative sign out the front. Root k over m t plus a phase. And then, now we already have this root k over m in the front here, so that you can imagine that there. But then by applying the chain rule again to this, you get another root k over m. So this will bring a k over m to the front. Now why this is a big deal, or what we've just seen by taking two derivatives of this thing, you notice that we get minus k over m times the thing that we started with. So this actually worked. This thing here is then x of t. Right? So what we've just shown is that this is actually a solution. Right? So now just looking at the parts of this thing, okay, so we have this function that's supposed to represent the position. If you remember from, say, your days in pre-calculus, this parameter here in the front, this constant in front of the trig function, is the amplitude. So this guy is the amplitude of the wave. Okay, so for us, we know that that amplitude actually happens to be d. If you look at the picture that I have, right? And so we can figure out based off of that like initial condition that where we started this thing, it's going to bobble back and forth between d and minus d. So the amplitude of this thing needs to be d, right? And so then what we would have going so far, so I'm going to kind of move up here a little bit. You know what, maybe I'll go one more line here. We'd have for us, we'd have x of t then is d cosine root k over mt plus a phase. Right. Now to find out what this other constant is, we can look at how we started things off. And so we've started things off, let's say if we start at time t equals 0, so we'll call this the initial position. Right, then what we know is that x of 0 equals d. Okay, so continuing with this expression, if we know that x of 0 equals d, then we can just force that to be true. So x of 0 also happens to be d cosine of 0 plus a phase. Right. Well, cosine of 0 itself is 1, and so then we can see if we make this phase equal to either 0 or 2 pi or 4 pi, then the cosine of those of 0 or 2 pi or 4 pi would be 1, and so then we would get d. So let's just set this phase equal to 0 to make our life simple. And so then for us, what we have finally then in all its glory, well, here let me say this, and therefore we can say the phase is 0 in this case. And so finally what we have is x of t, our position function, is just going to be d cosine root k over mt. Right? One final thing we can get from this, and hopefully you have some space, I'm going to actually erase this to clear out some room, is we can figure out how long it takes for this to cycle back to the same position. So if you start it here, you let the trig function run, it oscillates over here and then it oscillates back. This cosine function repeats every time this part of the function reaches a multiple of 2 pi. Okay, so what we can do is we can say this repeats when root k over mt is actually equal to 2 pi. So the time that it takes to repeat, we can now solve for. So the special time that it takes to repeat, and since it's a special time, I'm now going to capitalize this t, is going to be 2 pi square root of m over k. Right? So we got to bring this over to the other side. Right? So this is the time to cycle back and forth once, or this is the period. Right? Now, a couple things to notice about it. First of all, just to make sure it makes sense, if this thing were super heavy, right, it would have it has more inertia. If it was a massive object, it would be harder to wiggle this thing back and forth. So of course, if this is heavy, it should take longer to go back and forth. So that is there. This K is the stiffness of the spring. Well, if the spring's super stiff, boy, it should jiggle back and forth really fast or have a short period. So if K gets really big, the period goes down. Now, what's almost as interesting as what is here is what's not here. And that is, notice there's no dependence on how far you pulled back. So a big key with this thing, and I always, for my students, I'll draw a little skull and crossbones as something to look out for, okay, is notice there is no dependence on the amplitude. Okay, so if you pull it out farther, yeah, there will be a bigger force on the thing trying to get it back, but it also has farther to go. And so those effects kind of conspire to cancel each other out. And so it doesn't matter whether you pull this thing just a little bit and let it boing, boing, boing back and forth, or if you pull it out farther, there's no dependence on the amplitude. Okay, so again, just hitting the high points, start with F equals ma. Write A as the second derivative of position. That way everything will be in terms of position. This particular differential equation you get where you take two derivatives and you get the same function back with a constant, negative constant in front, that's going to give you sines and cosines. That's going to lead to oscillations. You might see as an undergrad, instead of writing it as sines and cosines, you can actually write it as complex exponentials, but that's something you can learn later on. And then from that, you get this solution that has a general form. You could pick sine or cosine, it doesn't matter, because you can always shift it with that phase that we found. This will be the general form, a cosine root k over mt plus a phase. You could have chosen sine here, but then that will play around with the phase that you'll end up with. So that is the mass on the spring.